Hi everyone, I am Prajwal Vasatti. Today I am going to discuss on the topic programming techniques for Turing machine. In today's video, we are going to learn how Turing machines are programmed using simple but powerful techniques. These ideas form the backbone of how computers work at the theoretical level. Let's get started. Introduction to programming techniques for Turing machines. A Turing machine is a simple but extremely powerful mathematical model of computation. Even though it looks basic, it can simulate any modern computer program given enough time and memory. So why do we need programming techniques? Because when TM gets complex, we need a structured way to design them, just like how real programming uses function and modular code. In this chapter, we learn three key techniques. First, the storage in state, and the multiple tracks, and the subroutines. Storage in the state. Turing machine can store temporary information inside the state itself. For example, instead of just using state like Q1 or Q2, we can use compound states such as Q, A, B, C. This acts like a small internal memory inside the TM. Why is this helpful? We can remember symbols without going back on the tape. We can compare the current symbol with previously seen symbols. We can store markers or flags while processing string. Here in the figure 8.13, a Turing machine viewed of having finite control storage and multiple tracks. Here the tape is like a spreadsheet where each cell can have multiple layers. For example, track 1 has the X, while track 2 having the Y, and the last track 3 is for the Z. This allows the TM to store the original input on the one track and temporarily marks on another without overwriting anything. This is extremely useful for pattern matching and comparison task. Next, TM that remembers the first symbol. Here we look at the example 8.6. Here, a simple example of storage in state. The TM reads the first symbol, either 0 or 1, and stores it in its state. Then it scans the rest of the string. If the same symbol appears again, the TM rejects. If the symbol does not appear again, then the TM accepts. So the TM accepts only those strings where the first symbol appears exactly once. Here is the important point of the TM remembers the first symbol. Next, multiple tracks and example 8.7. Now let's look at a bigger example. Using multiple track, the TM recognizes the language. This is not a context free, even though it is not a context free, but a TM can recognize it. It can recognize it. Track 1 stores the input. In the track 1, it stores the input, while track 2 stores markers for matched symbols. The TM marks each symbol in the left part and finds it matching symbol at the right part. It matches at the left part, then whenever it finds its matching symbol, it goes from the right part. The string is accepted only if the symbol matches perfectly around the C. Next part, figure 8.14. Here in the figure 8.14, just like real programming languages use functions, a TM can use subroutines. TM can use subroutines, small reusable introduction blocks. The copy subroutine is one of the most important example, because mark one symbol in the block of zeros, move to the end of the tape, copy the entire block of 0 to create a duplicate one, return to the starting point, continue the main program. The subroutine is used to perform multiplication in the Turing machine. Multiplication. The multiplication Turing machine takes input of the form 0 to the power m 1 0 to the power n 1 and produces the output, which is 0 to the power m multiplication multiplied by n as an output. How does it works? The first block of zeros represents m, and the second block as n. For each zero in the first block, the TM calls the copy subroutine once. The subroutine copies the second block at the end of the tape. After repeating this process m times, we get m multiplied by n zeros. Finally, the TM clears. After it cleans up the extra markers and halts with the correct output. As we explained the above, the example 8.14 and the 8.15. Here we can view the figures of the 8.14, the subroutine copy, and the 8.15, the complete multiplication program use the subroutine copy.
Thank you.